This is help for the homework on intermediate circuit analysis. I'll go over 3 or 4 of the design problems at the end of the homework, the ones that don't have answers provided. I'm not going to do the problems exactly. I'm going to do the same type of problems, but with different numbers. This first one is like number 26. You're given the voltage on a battery, and you're told that if the current out of this battery is bigger than 15 amps, a fuse will shut it down. And we'll learn about what fuses are exactly later, but what you have to know is that if the current gets bigger than 15 amps, this fuse breaks and all the current stops. The entire circuit shuts down. And so the question is, every light bulb you have is 25 ohms in resistance. How many of those can you connect in parallel without triggering this fuse and shutting down the circuit? And I put in parallel because when you plug things into your house, into the outlets in your house that look like this, outlets that look like that, you're adding things in parallel. You're never adding things in series when you plug into outlets in the house. It's always in parallel. So it's a very realistic type of problem. There are several ways to do this, so you could program a computer to do it, but the best way for you to do it at your stage is one at a time, just kind of using common sense and playing with it, starting with just one light. That's the smallest number I could attach. So let's look at what happens if I put one light attached to the battery. Remember, this has a resistance of 25. Look what you can immediately figure out. You can figure out what? You can pause the video and answer these questions yourself, of course. What can you figure out? Voltage is 100. Resistance is 25. So this is 100 volts. Resistance is 25. So you get that through this light, the current is 4 amps. Well, that's still less than 15, so we can keep going and try to put in a second light in parallel. So all this stays the same. We've added a second light, and this is what happens when you plug things into an outlet in your home. You're adding devices in parallel. So what would the voltage be on this light? Well, you can use the loop law, Kirchhoff's loop law, go around this loop, 100 volts of gain, so this has to be 100 volts loss. So this again is 100 volts. And now see how easy it is. Every time you add a light, it's always going to have 100 volts. And all these lights are identical. So you're always going to get the same thing. This is 4 more amps. By the way, this is one of the reasons we plug things in parallel in our houses. We can be guaranteed that everything we plug in will have the same voltage on it, so that's very predictable, so we can make our devices with that in mind. So what's our total current now? Well, 4 down this way, 4 down this way, so now the current here is 8. So these two together make 8. So you can see how this is going. Every time we add a light, we're adding 4 amps of current. So let's add one more light and see what we would get. We'll go faster. Okay, R equals 25. V is 100 volts. And so once again, you get a current of 4 amps. And when that gets added with this 4 and that 4, we now have a total current of what? 12 amps. Still under 15, and you can think of if I added one more, how much would I have? If I added one more light, well, I'd add another 25 ohms, 100 volts, so I would add another 4 amps into this group, and I would get 16, and that's too big, that's bigger than 15. So that means the number of resistors or lights we can add in this circuit in parallel is 3. All right, the next problem is like number 27 on the homework. And this is a tricky one. You may try to come up with some way to automatically do it as if you program a computer. But it's better if you just play with it and reason it out. And very soon we'll learn simple rules for resistors in series and parallel. And you'll be able to do this more quickly using that. But still, any electrical engineer should be ready to kind of play with things and puzzle them out. So let's look at this 24-volt battery. Okay, we want the current out of that battery to be 3 amps. So let's write that on here right now. That's what we want. I equals 3 amps. And then every resistor we have is 6 ohms. We have to make some arrangement where when we put it here, this will be true, that we have 3 amps going into that arrangement. And between here and here, you'll have a voltage drop of 24 because that's what's on the battery. So these are our 2 requirements. Now you'll learn faster ways to do this as you learn more formulas, but you still should be able to reason it out. There are a couple ways you can reason this out. I'll give you one way, but you can experiment with others. Let's say we put 1 resistor here. So just guess and check. 1 resistor and see what happens. And if it doesn't work, you can always erase it and try something else. So what happens if you put 1 resistor there? let's see what you can figure out. You know that the current is going to be 3 amps, and you know the resistance is 6 ohms. And so what do you immediately know about this? You know that the voltage on this would be 18 volts. Well, that's good. That's not more than 24, but it's not enough yet. So look what we know now. We know that in this part, what do we need the voltage to be? Between here and here. If that's 18 volts, what do we need this to be? We need this to be 6 volts. So we have 6 ohm resistors, and we need that to be 6 volts. That means we need a current to be 1. Well, we can't suddenly magically make the current change from 3 to 1, but we could split a current of 3 amps into 3 equal parts. And then we know for sure that the current on each part would be 1. So we could do that. And through each of these parts, you have I equals 1, I equals 1, I equals 1. Because there's no reason more would go down one branch than another. It's 3 amps of current coming in. These resistors are all equal. So there'd be 1 amp of current in each resistor. Remember, this is R equals 6, 6, and 6 ohms because every single resistor is 6 in this problem. So look what we've created, a situation where you have a current of 1 and a resistance of 6. And so that means that's forcing the voltage to be 6 volts. That's one way to do it. There are other ways to do it. We'll learn how to take this 24 and this 3 and calculate that we need a total resistance of 8 and how to do that. There are other ways to create multiple branches and do it, but this is one way. And you see what we did? We just played with it and guessed and checked, and if that doesn't work, you erase it and start over and try something else. I'll keep those problems pretty simple. So even if you just start guessing and checking with 1 resistor, then 2, put them in a row, then put them side by side and play with it. Even if you just guess and check every possible combination of 2 or 3 or 4 resistors, you'll eventually get it. All right, here's the last problem. It's like number 30, but if you can do number 30, you can do number 28. It's a 2-part problem. And that can be hidden because the actual problem can be hidden from you because the actual problem is all words. The problem won't be written like this. It's written in words. It says if you connect a light to a 30-volt battery, you get a current of 15. That's too much. The light burns out. You want the same battery and the same light, but you need the current to be only 3. All that will be in words. It won't actually make it clear that these are 2 separate circuits, but it's clear they are because you have 2 separate currents. So this is telling you to draw this circuit first. So 30-volt battery connected to a light whose resistance we don't know, but we do know that the current is 15. So you see what this is doing. When you feel stuck, let's say you set this up and you don't know how to get to the answer. If you can't find the answer, what should you do? You find what you can, right? And so what this is doing, this first part is setting it up so you can find that value of R. That's why all this information here, that's why they tell you what I call the bad circuit before they tell you the good circuit. In the bad circuit, you managed to measure that the current was 15 before the light burned out. And that can happen. It may take a little while for a light to burn out. Or we could say it's too bright and it's in danger of burning out. That's probably more realistic. You can often tell with an incandescent light bulb when it's just too bright and you have too much current going through it. So this current is too much. The light is going to burn out. But look what this information this gives us. This gives us the resistance of the light. 30 volts, 15 amps. That tells us that the resistance of this light is 2 ohms. So we just found what we could. We find what we can. And now we're going to take that and we're going to use it in this problem. R for the light bulb is 2 ohms. All right, so look what this says. This is one of the main purposes of the thing called a resistor, is to reduce the current to make things safer for the other devices. So we want the same battery, so put 30 volts. We have the same light bulb, and now from this part we know that its resistance is 2. And it says sketch it with a resistor. Now if we put the resistor in series with this, it'll take some of the voltage. We'll have some voltage here and some voltage here, so the voltage on the light will be smaller. If you put the resistor in parallel beside it, this would still get 30 volts and you'd still have this bad situation. So to reduce the current through, and we want to know, we'll call this RL for R for the light. We want to know what that is. There's one more given. that we need to write on our diagram. The current in this good circuit, the safer circuit, is 3. All right, so let's write that on here and see what we can find out. We'll switch to red for the things that you would figure out in this problem. I equals 3. I equals 3. Now we're doing intermediate circuit analysis, just like the problems earlier in the homework handout. We have a current and a resistance. We have a current, and we need the resistance. So anytime you see 2 out of 3 on something, you should jump on that right away and find the missing part. So if we have a current of 3 and a resistance of 2, that's telling us what? The voltage is 6. All right, so how can we use that? Try the next step on your own. 30 volts here, 6 volts there. That means this voltage must be 24 volts. By the loop law, gain 30, lose 6, so you must lose 24 across the last part. Now we see 2 out of 3 items on this resistor, so we're going to jump on it, right? 24 volts, 3 amps of resistance. That means this resistance must be 8 ohms. So we've answered both parts of the problem. We've sketched the circuit, and we've answered what the resistance of that resistor has to be to bring the current down to the acceptable level. And remember, you can always draw the pi to make the algebra go faster. V on top, I and R side by side, and you cover up the one we want. Here we wanted R, so we cover up that, and it tells us V divided by I.